Sponsored by Panasonic. Smart factory solutions for any mix, any volume. Introducing the new NPM W2S, the ideal placement solution for manufacturers who value reduced setup and changeover time over volume.
Welcome to the Indium booth here at SMT AI. I'm joined by Chris Bistecki, who is the Global Marketing Manager for the PCB assembly products. Welcome, Chris.
Hey, good to meet you, Trevor.
Okay. So we're here to talk a little bit about this low temperature solder phenomenon. There's a number of different approaches to it. Most of them have really come around through the relaxation of the RoHS regulations last year on bismuth. Can you tell us a little bit about your perspective on it?
Yeah, the low temp initiative probably started, I'm going to guess, really 4 to 5 years ago. And it's been building momentum and a lot of interest. And there's several drivers for it. You know, minimized package warpage is really one of the strongest drivers. And all the solutions have involved tin-rich alloys. And, you know, because basically they offer the melting range that everybody wants. They like to reflow at around 180, 190, and they offer that. Mm-hmm. So that's kind of ideal for processing. The bad news is those alloys aren't so ductile. I think the best way they're so brittle that if you take a circuit board made with them and you just torque it a bit, you can break a lot of those solder joints. So
this is through the bismuth, really.
It's the bismuth, you know, and people have tried to reduce the amount of bismuth in the alloy. There's been a lot of different approaches. You know, we've really tried doping it, doping with copper, doping with other things, and they've all given incremental improvement. But the bottom line is that alloy system is just extremely brittle. Mm-hmm. And, you know, you're forced to do things that are very expensive, like, you know, you solder your BGA and then you stake it with some type of a, you know, something to absorb the shock on the corners, so like a corner bond material. So, again, you can do that. It's just expensive, and you're kind of trying to make up for the failure of the bismuth-rich alloy. So what we've done at Indium, which we've got a lot of material science people, and that's what their thing is, and these are people that get really excited about material advancements, and we challenge them to come up with something that would give the low temp performance that they want without this brittle nature of the alloy.
So you've been somewhat successful in that by bringing out this new alloy, which is called Durafuse. Tell us a bit about Durafuse.
So Durafuse LT, the product. So we sell it as a solder paste, and it's a blend of powders, mm-hmm. and the different powders have different properties. And when you reflow them together, when you reflow them the first time in a reflow, you have some parts reflowing at a lower temperature, then the middle, then you have finally parts at the higher temperatures. But then that resultant joint you get, the unique thing about it is that resultant joint doesn't have any of the low temp phases afterwards. And it doesn't have the brittle nature. So it's solid. Next time if you'd reflow it again, you wouldn't see peaks until much higher. You couldn't reflow it again. But by the way, I didn't say, we would reflow this product, Durafuse LT would reflows in the range of 200 to 210 Celsius would be the peak temperature, which is, you know, much lower than normal, which might be 240 to 250. So
it's getting down there, but, you know, I mean, we still want to get like sub 200 if we can.
I mean, it would be good, but it's no good if the resultant solder joint cracks. So what we've done is come as close to the 190 goal that we can and still deliver performance needed by the end-use application. Mm-hmm. So as an example, what I'm describing, if you take a normal, let's say a bismuth tin silver alloy, just a conventional one, depending upon the drop test you do, because there's a lot of different ones, you could break that on the first drop. You drop it from, you know, a couple feet up, let it hit the ground, the solder joints just break first off. If you take like SAC 305 and do the same thing, you might get 100 drops out of it in the same test. So the magnitude difference is so big. And when people fine tune it, they might get maybe 2 drops at best. again, it depends on the test you do, but it's just an incremental improvement.
So what drop testing system, first of all, have you used, and what results have you got from it?
So what we do is we take the circuit board, it's populated with BGAs on one side, the other side has nothing. So we put the populated side down and the unpopulated side up, and then we'll drop a ball onto that circuit board that's suspended, it's held in place, and we'll see how many times you could drop that ball until it breaks.
That's a predetermined weight of ball, so you can get like a 50-gram ball or a 100-gram and so on.
Correct. I mean, you could have 44, 50 grams, 60 gram, that can be a range, but you always drop it from the same height, and then you measure the result. When we did it, I think with a 44-gram ball from 500 millimeters, I think we got like the normal bismuth tin silver, we got maybe, I don't know, I think it's 25 to 30 drops before you got a break. When we took Durafuse LT and we did it, we got over 3,000 drops, and it never broke. So then we redid the test with more weight. We said, okay, let's put on, I don't know what it was, 50 or 60, maybe it was 60 grams. And then we couldn't even test the normal bismuth alloys. We couldn't even test them because it broke first time. So you couldn't get a nice Weibull plot out of it. So we tested versus SAC 305, and we're actually comparable to SAC 305. We know that if you reflow the Durafuse LT at 210 for 60 seconds, which is kind of a typical time, we can get equivalent performance to SAC 305 and drop shock. So it's a very tough alloy.
Did you test against SN100C as well? That alloy?
We did not test against that, but generally that's, well, that might be, let's see, it's low silver, it might be incrementally, but we didn't test against that.
So that's interesting. So you've really got a very resilient alloy there for low temperature. So is this something that's available now, or is it something that's still going through testing?
Well, we're announcing it here. So we do still have some critical testing to do. We want to understand that reflow range between 200 and 210. If we can maybe have a longer time above liquidus at 200 would be acceptable. We don't know the answer yet. So we're exploring those boundaries of the process. And then we're also exploring, we want to do all the thermal cycling and get all that completed. So we have some more testing to do, but this is kind of where we're announcing it. And you know how new products are. You test them for a long time, but we're going to market. We're starting, right now we're already working with a couple partner customers who are evaluating it.
Well, I know that you obviously, to make this happen, you've had to add some special alloy into to be able to offset the brittleness of the bismuth. But of
so
course,
there's no bismuth in this.
Right, there's no bismuth in this.
No
Nope.
bismuth.
Really? Okay, that's interesting. Wow. Good. Well, we wish you a lot of luck with it, and look forward to hearing more when you get some testing results.
Excellent. Look forward to it.
Okay. Thanks very much for joining us, Chris. Bye-bye.